When even a Nobel Prize winner in physics doubts our current understanding of the universe, everyone knows that the astronomical hour has come. However, Adam Rees is not the only one at his wit's end. The James Webb Telescope is currently detecting more and more new structures in space that are in stark contradiction to conventional cosmology. But how can it be that the existence of galactic structures previously considered absolutely impossible is being confirmed? What do these puzzling findings mean for future research, and have our previous theories finally had their day? Many simple questions require very tricky answers. For instance, while the question of how fast the universe is expanding may sound extremely simple at first, it actually goes to the heart of a research mystery that has had experts racking their brains for many years. It is now considered certain that the universe has been continuously expanding since its birth around 13.8 billion years ago. As a result, galaxies are also moving away from each other at a speed proportional to the distance separating them. In other words, if Galaxy A is twice as far away from Earth as Galaxy B, its distance from us is also growing twice as fast. The American researcher Edwin Hubble was one of the first to recognize this correlation. To calculate how fast two galaxies are moving away from each other, you need to know their distance and a constant by which this distance is multiplied. This is where the so-called Hubble constant comes into play, and this is also where it gets extremely confusing. There has long been a major dispute among experts about how large this constant actually is, as previous measurements have produced completely contradictory values. In other words, the results we obtain depend on the measurement method used. One of these methods is based on the cosmic microwave background radiation, an almost isotropic relic from the early days of the universe, which is regarded as outstanding evidence for the Big Bang theory. Using the expansion rate of the universe, this method yields a value of around 67 kilometers per second per megaparsec. To put this into perspective, 1 megaparsec corresponds to 3.26 million light years, with 1 light year equaling around 9.46 trillion kilometers. Conversely, if we use so-called seeds to measure distances in space, specifically, a certain type of star in which the fluctuations in brightness are strictly periodic, the expansion rate is suddenly 73 kilometers per second per megaparsec. Thus, the universe appears to be expanding faster in our vicinity, up to a distance of around 3 billion light years, than in its entirety. This discrepancy between different values is referred to as the Hubble tension, and so far no researcher has been able to explain this unexpected deviation. The James Webb Telescope has taken aim at this enigma. Some scientists had previously hoped that the mystery surrounding the expansion rate was due to a measurement error by the Hubble Space Telescope. Adam Rees also wanted to determine whether an error had crept into the Hubble datasets. The physicist from Johns Hopkins University in Baltimore was awarded the Nobel Prize in Physics in 2011, along with other researchers, for discovering that the expansion of the universe is accelerating. His team used the James Webb Telescope to investigate the reasons behind the Hubble expansion and to uncover any Hubble measurement errors. So, how do you determine the expansion of the cosmos in detail? The so-called cosmic distance ladder is used for this purpose. Each stage of this ladder is based on the previous stage, so a potential measurement error runs through all stages. The seeds mentioned only prove to be reliable up to a certain point. As the distance increases, it becomes more challenging to measure accurately because the light from the seeds mixes with light from other stars, making them relatively difficult to see. However, Webb is 100 times more powerful than its scientific predecessor Hubble, allowing experts to look further and in more detail than ever before into the remote secrets of the universe. The new study published in the Astrophysical Journal Letters painted a rather sobering picture. The JWST covers the entire area previously observed by Hubble and found no measurement errors, so the problem of Hubble's tension still remains. Adam Rees has a brief but profound explanation for it. It could be that we have simply misunderstood the universe. Furthermore, we must now find out whether we have overlooked something in our previous investigations and how we can connect the beginning of the cosmos with the present. This solution calls Einstein's theory of gravity into question. Researchers around Adam Rees are not the only ones working on the confusing Hubble tension. Some scientists from the universities of Bonn and St. Andrews have also approached this mystery and found a new possible explanation. In detail, our blue home planet is located in a bubble-shaped region of space with relatively little matter. The density of matter is higher around the cosmic bubble, and gravitational forces emanating from this matter pull the galaxies in the bubble towards the edge. As a result, they are moving away from us faster than would actually be expected. This is a perfectly plausible explanation, but one that leads straight to the next research dilemma. The Standard Model does not provide for such bubbles or underdensities. They should not exist at all. Instead, matter should be evenly distributed in space. At its core, the Standard Model is based on a theory by Albert Einstein on the nature of gravity. However, it's possible that gravitational forces behave differently in reality than Einstein predicted. The scientists therefore referred to a modified theory of gravity presented by the Israeli physicist Moti Milgram in the 1980s. However, the so-called modified Newtonian dynamics has not yet achieved more than outsider status, even though it accurately predicts the existence of the corresponding bubbles. Assuming that gravity really does behave according to Milgram's ideas, all the discussions about Hubble tension would also be a thing of the past. In this context, there would actually only be one constant for the expansion of the universe, and the observed discrepancies would be due to irregularities in the distribution of matter. The future will have to show to what extent this new approach will be accepted and confirmed. A look into the cosmic past also shows how much still needs to be understood in the future. Sometimes a single value is enough to leave even the most experienced astronomers with open mouths. For example, the galaxy Jade's RGSZ 1-13-0 has a record redshift of 1432, meaning this gravitationally bound group of stars already existed 290 million years after the Big Bang. At the same time, the earliest known galaxy also raises some pressing questions. How could it have been so bright and massive at that time? Where did the necessary matter come from? Detected with the help of Webb's near-infrared camera, NIRCam, the structure likely took 100 million years to grow to its observed size. The bottom line is that this galactic infant contradicts practically all theoretical models and computer simulations for the very early cosmos. In fact, the galaxy is in the best of company. The 6 galaxies that the James Webb Telescope had already added to the star maps at the beginning of 2023 were also much more massive than they should actually be. Although these structures existed when the universe itself was only 500 to 700 million years old, they were already reminiscent of today's Milky Way. However, as this is simply not possible according to conventional cosmology, the galaxy Jade's RGSZ 1-13-0 earned the nickname universe breakers among experts. Instead of these unexpected baby galaxies, researchers observed impressive objects, all of which contained more than 10 billion solar masses of stars. One of them could even have a mass of over 100 billion solar masses. The question that now needs to be answered is how this was even possible. Because even if only one of these galaxies is real, it would push our understanding of cosmology to its limits. To explain the presence of these structures, the density of matter in the early cosmos would have to have been up to 5 times greater than our models suggest. Alternatively, the galaxies could have grown in a way that is completely unknown to us. But what do discoveries of this kind mean in a larger context? Does the history of the early universe and possibly the Big Bang theory itself need to be rewritten from scratch? Our current understanding of galaxy evolution is as follows. First, dark matter collapsed into giant clumps called halos within the first few hundred million years after the Big Bang. As a result, the gravity of the halos attracted normal matter, eventually forming stars and galaxies. However, this process took time. The matter would have slowly clumped together and gradually produced larger and larger galaxies. Within this model, the galaxies discovered by Webb are therefore impossible, and our previous theories do not predict nearly as many dark matter halos in the early universe as would have been required for the formation of large structures. Yet some experts are already finding it difficult to completely abandon the established research consensus of the past. This includes Julian Munoz from the University of Texas at Austin, who suggests that we might be better advised to interpret the data provided by Webb with a certain degree of caution. He points out that if there were indeed 10 times more dark matter structures in the early cosmos than previously assumed, there would also be 10 times more galaxies in the Webb images. However, this is not the case. Munoz and his team counted how many galaxies Hubble had seen over a wide range of brightness and found that the same discrepancy applies to the Hubble data. Thus, the halos needed to match the Webb data would throw the Hubble data into chaos. The question arises, Which telescope should we trust? There is no question that Webb is significantly more powerful than its predecessor, but it only began its scientific service in 2022. The Hubble telescope, on the other hand, has been gazing into the gigantic expanses of space for almost 35 years. According to Munoz, quantity trumps quality at this point, and the Hubble data seems more reliable for now. For this reason, it might be better to look for other explanations. For the strange early galaxies that do not require us to rewrite the entire history of the development of the universe. To expand on this topic further, let's delve deeper into the implications of the James Webb Telescope's findings and what they might mean for our understanding of the universe. The James Webb Telescope, with its advanced capabilities, has been instrumental in pushing the boundaries of astronomical observation. One of its significant achievements is its ability to observe extremely distant galaxies, shedding light on the universe's earliest epochs. The findings from Webb's observations are challenging our current models of galaxy formation and evolution. If galaxies existed earlier and were more massive than previously thought, it could indicate that our understanding of the universe's development is incomplete or incorrect. This situation presents a profound challenge for astronomers and cosmologists. The discrepancies between observations from Webb and earlier data from the Hubble telescope suggest that either the new data from Webb is revealing something fundamentally new about the universe, or that there might be errors or limitations in our current theoretical models. This could lead to a paradigm shift in our understanding of cosmology. In addition to the galaxies observed, Webb's infrared capabilities have provided insights into the composition and distribution of cosmic dust and gas. This data is crucial for understanding star formation and the processes that lead to the creation of galaxies. For instance, the infrared observations have allowed scientists to peer through dust clouds that obscure visible light, revealing the formation of new stars and galaxies that were previously hidden. Moreover, the new observations might necessitate a reevaluation of the role of dark matter and dark energy in the universe. Dark matter, which does not emit or interact with electromagnetic radiation, has been inferred from its gravitational effects on visible matter. If the structure and distribution of dark matter in the early universe are different from what current models predict, it could affect our understanding of its role in galaxy formation. Similarly, dark energy, which is thought to be responsible for the accelerated expansion of the universe, might also require adjustments to the theoretical framework that describes its effects. The discrepancies between the Hubble and Webb data also highlight the need for improved calibration and cross-verification of astronomical instruments. While Webb is a more advanced and powerful telescope, its observations must be validated against long-established data from Hubble and other telescopes. This process ensures that any new discoveries are accurate and reliable. In addition to theoretical implications, these findings could have practical consequences for future space missions and observational strategies. If the early universe was more complex than previously thought, future telescopes and missions might need to be designed to address these new challenges. For instance, next-generation space telescopes might need to be equipped with even more sensitive instruments to detect faint signals from the early universe and better distinguish between different types of cosmic phenomena. Furthermore, the new discoveries could stimulate interest in alternative theories of cosmology and astrophysics. Researchers may explore other theoretical frameworks that could better accommodate the new data. For example, theories that incorporate modifications to general relativity or alternative explanations for dark matter and dark energy might gain traction as scientists seek to reconcile their observations with theoretical models. The scientific community will need to engage in a rigorous and open debate about the implications of these findings. Peer-reviewed publications, conferences, and collaborative research efforts will play crucial roles in scrutinizing and validating the new data. As researchers analyze and interpret the observations from Webb, they will need to consider how these discoveries fit into the broader context of our understanding of the universe. The challenge of reconciling new data with existing theories is not unique to cosmology. History shows that scientific progress often involves revising or even overturning established theories in light of new evidence. For instance, the transition from Newtonian mechanics to Einstein's theory of relativity marked a significant shift in our understanding of space and time. Similarly, the potential need to revise our cosmological models in light of Webb's findings could represent a major leap forward in our quest to comprehend the universe's nature and origins. In summary, The discoveries made by the James Webb Telescope are pushing the boundaries of our knowledge and challenging existing theories in profound ways. The observations of early, massive galaxies and the discrepancies with previous data underscore the need for a reevaluation of our understanding of the universe. As scientists work to interpret these findings, they may uncover new insights that reshape our comprehension of cosmology and astrophysics. The quest to understand the universe is an ongoing journey, and each new discovery brings us closer to unraveling the mysteries of the cosmos.